So now we want to see if we can determine whether a system is invertible using the impulse response. So we'd like to determine if a system is invertible using the impulse response, and what we'll see is that you can do this sometimes. And to understand it in more detail, we'll have to wait till we discuss Laplace transforms, which is just coming up next, and then also Z transforms. So recall that a system G is called an inverse system for a system H if G of H of x is x. So that is, we put x through the system H, and then we take that output and put it through the system G, and then we get back our original signal x. If these systems are LTI, what we're saying is convolve H with x, and then convolve that with G, and you should get back x. And the same thing for discrete time, convolve H with x, and convolve that thing with G, and you should get back x. So one thing to note is that if I convolve x with the delta function in continuous time or in discrete time, I get back just x again. So since convolution is associative, basically what I can do is I can do G star H first, and then I have something called G star H, which when applied to x should give me back x. Or equivalently, G star H of t should equal delta of t, or G star H of n should equal delta of n. So really, the question is, can I find a system G, or an impulse response G, that when I convolve it with H, I get back the delta function, either in continuous time or discrete time? So let's do a quick example. Suppose we have this decaying exponential h of n, which is a third to the n u of n. We saw that this is the impulse response of a system with a recursive input-output relation. So that is, y of n is equal to x of n plus some past value of y of n, in this case 1/3 y of n minus 1. And remember, what we did was we just plugged this formula back into itself, and we got 1/3 x n minus 1 here, plus 1/9 y of n minus 2, and you continue along like that, and you'll get exactly this impulse response here. So what we have here is an input-output relation, which says, okay, here's x of n, I put it through a system H of n, and I get y of n, but now what we want is a y of n. If I put in y of n and I put this into a system G of n, I should get back x of n. So we can just rewrite this formula to have x of n as the output and y of n as the input. And looking at this system, we can just see that the impulse response is just delta of n and minus 1/3 delta of n minus 1. Okay, so let's plot this impulse response. 1 at time 0, and 1/3 at time 1. Okay, so looking at this impulse response, there's no positive values for no non-zero values for n less than 0, so that means that the system is causal. And if I look at 1 plus 1/3, this thing is less than infinity, so the system is stable as well. So this is a causal and stable inverse. So that seems great. We have an inverse system for this particular decaying exponential system. So what happens if G is unstable? That is, we can find an inverse system, but it's unstable. Well, we might be in trouble, because we might be in a situation where H star x is one of the input signals that causes the output of G to blow up. For example, we could take the differentiator. Y of t is the d dt x of t, and the inverse of a differentiator is an integrator, but we know the integrator is unstable. So should we really build the inverse system? That is, can we really build a system to recover our input signal? Or is it somehow that we've messed up the input signal by putting it through the system H in such a way that we can't actually recover it, because something would blow up if we had tried to do that? So similarly, if h of t was an integrator, which we know is unstable, the output y of t can become unbounded. So if you wanted to find an inverse for this unstable system, it would have to be able to handle an arbitrarily large input, which is probably not okay in terms of the engineering. In terms of, you want to limit. The reason you want bounded inputs is because you want to make sure that your devices that you're using to process the data, process the signal, are operating within the tolerance of the device. So another thing that can happen is, we saw before in the example that it was stable and causal, but you could also have a situation where the inverse is non-causal. So the simplest example of this is if h is the delay, a delay by n0. So that has impulse response delta of n minus n0. And the inverse system is just a rewind of n0, so delta of n plus n0. That's the impulse response of the inverse system. But this inverse system is non-causal. And why is it non-causal? Because to produce the output at time, n equals 5, I need to know the input at time 5 plus n0. And that's not possible unless I've already seen that input. So I can't do that in real time. And we talked a little bit about real-time operation of systems when we talked about causality. So we can also find more complicated examples where the inverse system has a non-zero impulse response for all n less than 0, which means I would have to wait for infinite time in order to get enough of the signal to do the inverse. So the one question is, are non-causal systems okay? I mean, you'd have to wait for all the output yn to be generated before you can apply the inverse. So are you really inverting the system? Or are you just kind of saying, well, let me produce this infinite length signal, and then I will process this infinite length signal and get back the original signal? Is that really inverting the system, because you're not doing it in a realizable sort of way? So this is the kind of question that we're interested in. So if we have to wait for all of the output y of n to be generated, this might be bad in terms of an implementation. So these issues are kind of complicated, and this shows why, generally finding an inverse system is a complicated operation. So we often want to call a system really invertible. We don't want to say that a system is really invertible if the inverse system is both causal and stable. And sometimes that goes under the moniker realizable. So this is a realizable system. And that sort of means that it can, in real time, invert the system. So the real issue here is that it can do it in real time. So the important thing to remember really is that when we go forward, we'll be able to write down inverse systems which are, we can show are, say, unstable, or inverse systems which are non-causal. And in this case, they're not realizable in this sense, but they still might be interesting to study, because you might be able to do the kind of approximations that we did before. We can take a non-causal system and try to approximate it with a causal system. So it's not just that only interesting to look at causal and stable inverse systems. But really, in order to really invert the system, truly invert the system, we're going to need the inverse to be stable and causal, because we want the output at time y of t at time t, at time t equals 5, it has to equal x of 5. And that's a big ask, especially if the signal is dependent on if y of t is dependent on a big chunk of x of t. So what we're going to do later on is we're going to look at example problems about invertibility when we talk about the Laplace transform, which is coming up next in this class. And so when we see that, we'll be able to try and get a better, more systematic way of understanding how inverse systems work.